Welcome back to Calculus 2. This is the second part of our lecture on Taylor and Maclaurin series. In the first part, we introduced what Taylor and Maclaurin series are. We looked at some examples for the functions e to the x, sine of x, and cosine of x in their Maclaurin series representations. In this lecture, we're going to look at some applications of Taylor-Maclaurin series, and then some theorems that tell us something about convergence of Taylor-Maclaurin series to their functions and power series representations. All right, we're going to jump right into it. Recall from part one, in the intro, we took the point of view, one way to introduce Taylor or Maclaurin series is building or generalizing off the idea of a linearization. So let's start with that. Let's say we have a function, same graph we had in the intro roughly. The function is f of x, and instead of asking to calculate the tangent line, let's stick to just talking about and thinking of a linearization. In other words, for this curvy function, approximating it at that point, x equals a on the graph, with a linear function. That's what we're calling a linearization, or a degree 1 polynomial approximation. Okay, so the function value and linearization value are approximately equal. They're close, so long as our x values stay close to a. We have this formula for the linearization, pretty much the tangent line formula. How we're going to tie this in to Taylor and Maclaurin series is by noticing those first two terms look like the first two terms in a Taylor series. And in fact, they actually are the first two terms, the n equals 0 and n equals 1 term. Now, if we were to keep going with terms in the Taylor series written down there, the next term would have a coefficient of the second derivative at a divided by 2 factorial times x minus a squared, and then that continues for the Taylor series representation. Well, how we turn this into a generalized approximation is, notice f of a is a constant term, f prime of a times x minus a, that's your degree 1 term. The next term, f double prime of a divided by 2 factorial times x minus a squared, that's your quadratic term. And basically, we can extend the idea of a linearization by including terms further in the Taylor series representation. Now, what we're calling a Taylor polynomial down here, or the Nth Taylor polynomial, is instead of approximating the function by a degree 1 polynomial, a linearization, we're going to approximate the function by a degree n polynomial, or nth degree polynomial. And that's what we call formally a Taylor polynomial, or nth Taylor polynomial. Notice in the expression for the nth Taylor polynomial, or denoting as p sub n of x, that is not an infinite series. Notice the highest power of x is x minus a to the nth power. So what we have here is a degree n polynomial. This is not an infinite sum, it's finite. It only contains a finite amount of terms. All right, now graphically, if you take a look at the graph up there now, what the idea of a nth Taylor polynomial, what that does for us is, instead of approximating at that point on the graph, a comma f of a, instead of approximating the function with a degree 1 polynomial, or a straight line, since the function is, sufficiently curvy there, we should probably try to approximate it with a curvier function instead of a straight line. And that's exactly what the nth Taylor polynomial does. Recall some basics of algebra. Nth degree polynomials they kind of have a lot of turning points. And the graph can have a lot of different peaks and valleys, local maxes and local mins. So here we can approximate it with a reasonable looking sketch there. This is not accurate, but just a representation, so you can kind of get an idea. We can approximate this function by a curvier polynomial over a larger value range of x. So instead of just approximating only very close to a with a linear function, notice we kind of extend the range of values for which this approximation seems valid over a larger portion of the graph. Okay, that's the perspective we're going to take for Nth Taylor polynomials. They are an extension of the linearization that you saw back in Calc 1. So instead of approximating by a degree 1 polynomial, something that contains just x minus a, we approximate the function with an nth degree polynomial that contains x minus a to the nth power. All right, this is going to lead you down the path of getting to some engineering applications in applied mathematics. But let's take a look at a simple example, one that we kind of already did the work for. So before we move on, notice in your definition of the nth Taylor polynomial there, it is pretty much the same idea of a Taylor or Maclaurin series. We calculate the coefficients of this degree n polynomial by calculating nth derivatives. Now we're going to use an example where we basically did all the work. We're going to look at a nth Taylor polynomial for sine of x, so that way we can see what the applications of are with a simple example that we've already done. So let's take a look at example 3. The question is going to ask us to use the fifth Taylor polynomial, or fifth degree polynomial approximation of sine of x at 0. So this is kind of a Maclaurin series version. And we're going to use that fifth degree Taylor polynomial sine of x to approximate the function value sine of 0.2. And again, in calculus, we by default interpret the input to trig functions as being angles in radians. So we're approximating here sine of 0.2 radians. All right, now our starting place for this, since we're asked to find a Taylor polynomial at 0, let's take a look at our Maclaurin series for sine of x that we came up with in the previous part. So we had this version here. One thing to point out, for an nth Taylor polynomial, the highest degree is n. Here, if we're asked for the fifth Taylor polynomial, we have to have a polynomial that contains only terms up to x to the fifth, or a fifth degree polynomial. And that is pretty much the first 3 terms in that Maclaurin series for sine of x, x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. Those 3 terms are what we're going to call the fifth Taylor polynomial of sine of x. So we basically calculated that in the previous part of this lecture. So we have the fifth Taylor polynomial here. What I want to do is take a look at a visualization for what these Taylor polynomials look like before we move on to finish this problem. So we have the fifth Taylor polynomial here. Notice it's a degree 5 polynomial. Let's take a look at how this polynomial relates to the graph of sine of x. This might be a little bit hard to see in the colors, but the darkest shade of blue there, you can kind of see it, is the graph of sine of x. And then in orange is the first Taylor polynomial. And if you were to calculate the linearization of sine of x, you get a function that looks like P1 of x, that looks like the graph of y equals x. And as it turns out, the linearization of sine of x is just x. So we see a linear function in orange for the first Taylor polynomial of sine of x. All right, The kind of medium shade of blue is the third Taylor polynomial of sine of x, approximating sine of x by a degree 3 or cubic polynomial. And you can kind of see the approximation from orange, a straight line, looks a little bit better now as that degree 3 cubic function. The final one that we're going to look at in this sketch is the fifth Taylor polynomial, which, at least over these range of x values we have sketched here, which is a degree 5 polynomial. As you increase the degree in your Taylor polynomial approximation, it kind of more accurately resembles the graph for sine of x over a larger interval of x values. So the only thing I want you to take away from this visualization is how the fifth Taylor polynomial kind of looks very close to the graph of sine of x. It looks like a much better approximation than just the first Taylor polynomial in orange, which would be p1 of x equals x, if you were to calculate that. All right, so that's just a visualization to see how the Taylor polynomials relate to the function for various orders. So let's go back to the problem. We're basically just going to manipulate and plug in a certain value to our fifth Taylor polynomial, p sub 5, that we have there. And what we want to think is this Taylor polynomial, like a linearization, is a very good approximation to the function value, so long as we're close to our approximation point, which we were doing in an approximation, a fifth Taylor polynomial sine of x at x equals 0. And if you take a look at what we're approximating, sine of 0.2, your input, 0.2, that's sufficiently close to 0. All right, so what we should find here is that this fifth Taylor polynomial, evaluated at 0.2, should be pretty close to sine of 0.2. All right, if you plug that into the fifth Taylor polynomial, replace all x's with 0.2, you get this value 0.198669333. All right, that's pretty tedious, but that is your value for the fifth Taylor polynomial, which should be a reasonable approximation to sine of 0.2. Now, since calculators are the be-all, end-all of numerical values, calculators are always right. Let's see what our calculator tells us. So if we were to take our calculator, make sure you have it in radian mode. The derivative of sine of x and cosine of x, those results are only valid if x is in radians. And if you plug in sine of 0.2 radians, you get a remarkably close value to what we found with our fifth Taylor polynomial. It is pretty much almost the same up until that very last decimal place, at least of what my basic scientific calculator was able to display. It is practically the same value for all purposes related to science and engineering. So what we get here is a very or extremely accurate approximation to sine of x using a fifth degree polynomial approximation, a fifth Taylor polynomial. That's how in practice in your physics, maybe P-Chem, physical chemistry courses, in some of your engineering courses, we'll use Taylor series and Maclaurin series to approximate certain complicated functions and function values. We'll save that for where it pops up in those courses, but here we have a very simple application of that just to approximating sine of 0.2. All right, kind of the last part for this lecture are going to be what we get to with some theorems that address some theoretical questions that we need to address for those of you continuing into higher level mathematics. Some of your science and engineering courses aren't too concerned with issues of convergence, but for mathematics, you would be. So we have a few questions here. The two primary ones that the theorems we'll get to will address is this first one: when are the power series representation of a function and its Taylor series, when are they the same? Do they have to be the same? Should a power series representation that we found by manipulating 1 over 1 minus x coincide with calculating nth derivatives for a Taylor series representation? We'll see. A second question kind of comes off what we looked at in example 3. How do we know when an nth Taylor polynomial is a good approximation? Now, we saw in example 3, just by comparing kind of the numerical value from a calculator for sine of 0.2, that we did have a very accurate approximation. But how would we think of this in general? So how do we know when our nth Taylor approximation is a good approximation? We'll have a theorem or two that says something about that. That would also be relevant in applied mathematics, where you apply certain other approximation techniques. You would want to know if your approximation is good enough. All right, let's go ahead and answer question 1. There's a theorem that answers question 1. And the theorem, there's not like a person's name attached to it, but the theorem could be titled the uniqueness of a Taylor series. Now, what the theorem says is if we have a function that already has a power series representation at a certain x value a, then that power series has to be the Taylor series of that function at x equals a. Now let's take a look at an example just to see how this relates together. Remember the main idea of Taylor and Maclaurin series, and they're both the same thing. A Maclaurin series is a special case where a is 0. Taylor and Maclaurin series allow us to calculate the coefficients with nth derivatives. We didn't mention any of that when we were manipulating 1 over 1 minus x to fit the form of the geometric series, which was how we were doing this before introducing Taylor and Maclaurin series. So let's take a look at an example that we could have covered earlier. If you're kind of up for it, maybe pause the video and find a power series representation for this function, x divided by 1 plus x squared. Right now, you can do that by manipulating 1 over 1 minus x. See if you can find a power series representation that way. We'll check in about a minute. This is very similar to examples that we did earlier when covering that. All right, welcome back. Hopefully that wasn't too bad. We're going to relate this to this theorem to kind of understand it with this example. First thing we would want to do to have it fit the form 1 over 1 minus x, let's pull that x out of the numerator. We'll write it as a factor. Recall you want in your denominator 1 minus something. So we rewrite 1 plus x squared in the denominator as 1 minus negative x squared. And at that point, that that fraction at the end, that now fits the form 1 divided by 1 minus something. The something is now negative x squared. So if we plug that in to what we've been calling the geometric series, we get this power series representation. There's a factor of x in front of the summation. And then we have within the summation, negative x squared all raised to the nth power. Now, if you simplify that by taking the nth power of negative 1 and the nth power of x squared, you'll get negative 1 to the n, and then you'll get x to the 2n power. We can take that factor of x out front, multiply that in, x to the 2n times x, or x to the 1, multiply those same bases, x, you can add their exponents to get x to the 2n plus 1 for this version. All right, so what we have here is a power series representation for the function x divided by 1 plus x squared. What this theorem says is that power series at the end there, since this is a power series representation in powers of x, this has to be the Maclaurin series for that function, x divided by 1 plus x squared. Now, I realize that might not be saying much, or you might not realize the significance of that, but if you were to calculate nth order derivatives, to calculate the coefficients, like you would with the Taylor-Maclaurin series, you'd find that they evaluate basically to -1 to the n for the nth coefficient of, in this case, a Maclaurin series. Go through that, try this problem by calculating the Maclaurin series. It's a little tedious by calculating repeated derivatives for x divided by 1 plus x squared. You get some very awkward expressions by using the quotient rule, but you'll find that they coincide. So this theorem says once we find a power series representation for a function, it has to coincide with being the Taylor, or in this case, Maclaurin series. All right, let's get to the second question, which deals about how do we know when our approximation is good. So we're going to take a look at a way to quantify when an approximation is good. So let's start with the function. We can write in a simple formula for a finite sum, an nth Taylor polynomial. It's basically a sum of powers of x. Here we're using the index as k, arbitrary index. Usually we use it as n. But notice up in the upper part, the final value for our index k is n. And that just coincides with what we were looking at earlier. The nth Taylor polynomial has to be an nth degree polynomial. And if we were to take a look at x minus a to the k power, when k equals n, that gives you x minus a to the n, which would represent the highest degree term, x minus a to the nth power, for an nth Taylor polynomial here. All right, so where is this going? Well, first, with what we based, starting off of the linearization, we said the function value and now the nth Taylor polynomial, they should be very close or approximately equal when your x value is approximately equal to a. So provided your x value is close to your approximation point, you should have pretty good approximations. Now, how do we actually quantify that? How good is this approximation? What we're going to take a look at is the difference between the true function value and the approximation value. And how we determine that is we take a look at this difference from the function value with the nth Taylor polynomial function value. Now, if our approximation is good, this quantity that we're defining and calling the remainder, if f of x and p sub n, the nth Taylor polynomial, are pretty close, that remainder should be very small. So how we define or quantify a good approximation is with a remainder that is small. Now, how small is small enough? That's kind of saved for your physical or engineering problems. But we're going to take a look at the mathematical version for what this remainder tells us. All right, now what we covered earlier with stating the Taylor or Maclaurin series, that was a way to calculate the nth coefficient with nth derivatives. What this theorem basically says, what we were mentioning right above, we want to find a way to quantify the value for our remainder. And that's what this theorem basically tells us. We have our remainder defined as the function f of x minus the nth Taylor polynomial. And ideally, we would want that remainder to be small for the approximation to be good. So what this theorem basically says is if we have p sub n representing the nth Taylor polynomial of a function at a, then for any x value within an interval containing a, that's usually our interval of convergence, there's a certain number between x and a, c, such that we can directly calculate the remainder. And what we have it is the nth remainder. So in other words, the difference between the function and our nth Taylor polynomial, it is an n plus 1 derivative. So the order of the derivative here is one more than what's in your Taylor polynomial, n plus 1. And that's evaluated at c. So what this theorem basically says is, provided we are working within the interval of convergence for the most part, there's a real number c for which we can directly calculate the remainder. And I realize this might all seem complicated, but it basically says your remainder is x minus a to the n plus 1th power. All right, now this kind of question requires two parts. So we have this theorem about calculating the remainder. But how do we relate that to it telling us something? This is the third part to answer, or I should say the second part that answers question 2, our third theorem, however. This theorem deals with the convergence of the Taylor series. Now this kind of brings it all together. This is going to kind of tie in what we were mentioning above with the remainder. The previous theorem gives us a way to directly calculate the remainder as a function of x. What this final theorem says is if we have a function that has derivatives of all orders, in other words, our function is sufficiently smooth. Remember, derivatives basically tell you where a function is smooth or not. Recall in Calc 1 the idea of differentiability. And if we assume a function has derivatives of all orders on an interval, then what this theorem basically says is the Taylor series converges to the function if and only if the limit for the nth remainder as n goes to infinity equals 0 for all x. So in other words, as we look at kind of higher order terms from the Taylor series, if the remainder goes to 0 as the order of the terms goes to infinity to 0 for all values of x, then the function and Taylor series are the same. In other words, the Taylor series converges to the function. All right, now these theorems aren't terribly important, in my opinion, to our course, Calc 2, but they do set the foundation for where higher level mathematics kind of goes from. Depending on how far you go, you might get to see kind of the generalized versions of these and maybe other approximation ideas in other mathematics courses.